can you hear me well? Okay, wonderful. So, привет, Минск! Как дела? Хорошо? Awesome, конечно. So, unfortunately, the rest of the talk will be in English because that was pretty much like 95% of the Russian that I can master. Maybe the last 5% is then like "Я могу, но не хочу," or also very important thing yesterday. So when I arrived, I had a very, very eager lady at the passport control, and she saw my old visa from last year and went like, "Your visa is not valid anymore." I'm like, "Нет." Going through the pages, здесь. And that's how I roll. Anyway, so I work at Archaeologic in Zurich as a software engineer, and at Archaeologic we do very serious things, and I'm a very serious person. I just happened to lost my luggage, so I'm not wearing a suit. No, as you may notice, I've been here before, and I would like to say thank you so much for the RSCONF team to make this all happen and have me again. Give a big hand of applause to the team for making this happen, because I think they're doing a great job. With that aside, you might wonder, why should I, as a front-end or web developer, care about computer graphics? And to quickly figure out who I am talking to, who knows computer graphics? Who knows what pixels are? You're laughing, but come on, that's not obvious. Who knows what RGB is? Who knows? Keep your hands up if you're gonna. We're gonna do this for a while now. Who knows what trilinear filtering is? Wow, that's more than I expected. Okay, so well then, you're gonna learn something new. You can just basically go have a drink or have a coffee, or just join me on stage and just have a seat on the sofas. They're quite comfortable. Anyways, so I think it's important to understand computer graphics because they happen all the time. Whenever we do something, whenever we shift things around, whenever we use CSS, in the end, pixels are going to be put on screen. And if we do it wrong, then you have to adjust your microphone. When you do it wrong, then it gets slow because you have to repaint a lot on the screen, and it gets Yankee, and you don't get 60 frames per second, and it looks shit, and people get angry at you. And the problem is, computer graphics is a super deep rabbit hole. So normally in university, you have a course of at least 6 months to actually learn all this crap. I have 50 minutes. But it's going to be fine. I'm going to gloss over the less interesting bits and pieces. Also, you have to understand that there's graphical performance, or performance in making things fast and making things snappy and nice and smooth, is actually a bunch of trade-offs that you have to make. You have to understand what you're doing to know when to use what. Like, should I use the GPU here? Should I use the CPU here? Should I actually sort of not do this one animation now, but actually try to do it later? How do I do this without actually overflowing what the computer can do? And on the web, that is particularly tricky, because on the web, you never know what computer or device you're on, right? It can be a potato with Internet Explorer 5. And good luck getting 3D on there. All right, so are you ready? Очень хорошо. Correct answer. All right, so let's go. So first of all, we're gonna figure out what the hell actually are pixels, like literally. What is this? Because that you all laughed, so I can probably gloss over that one, right? But I'm not. And then we're gonna go into what's basically goes into putting them on screen. How do I get colors on the screen, right? How do I make this happen? And then we're gonna see how the browser does the more, well, basic things. So how do we actually get website content on screen? How does the browser do this? How does the browser make sure that my code runs as well as possible? How can I help the browser run my code well? And then we're gonna quickly gloss into 3D graphics, which is a really interesting topic. Come talk to me afterwards, because I'm already really gonna gloss over this one. So pixels. That's a pixel, and we've got lots of them. And each pixel obviously has 3 components. There's a red dot, there's a green dot, there's a blue dot, and that makes colors. Okay, cool. But now I have this physical screen. and the pixels. But how does that look on the computer? Like, how does the computer know when to switch them on and off? That's working via, whoops, that happens via using a piece of memory, because we have to store the colors somewhere. And this memory is usually referred to as the VRAM, the Video Random Access Memory. So that is a piece, most of the times it is a dedicated piece of memory. It's not with the rest of the RAM, but especially on mobile phones, that's not true. It's just a normal piece of RAM. And then there's a thing that takes the values that we store in memory and puts them as colors on my screen. And that's our graphics card or graphics chip if you're using a phone or something, a laptop. So we have a bunch of ones and zeros, magic, and then pixels. Okay, cool. The magic is called the GPU. All right. So let's have an example. Here we have a very simple 3x3 screen. So this is one pixel that is red right now. This is one pixel that is green right now. This is one pixel that is blue right now. And then we have this 3 times in a row. It's a very simple screen. In memory, this looks like this. So we have 3 values, red, green, blue, for each of these pixels. And then we get the previously shown image. And then there's obviously the question, like, how do we store this? Like, how much data does it need in memory? And why does that actually matter? We're going to see why that matters in a second. So there's a thing called color depth. And you might have heard like high color or true color or 256 colors and stuff, and 16-bit color, 8-bit color. What does that actually mean? It means how many different shades of one color component can I actually store? How many shades of colors in general can I store? And here you see, like, with 24-bit color, you actually basically have one entire byte, so 256 shades for each of these color components, red, green, and blue. But you don't have transparency, so you add one more, you get to 32-bit. That also allows you still 256 shades of gray. But it also allows you to actually have sort of 256 different transparencies as well per pixel. But how much memory is that actually? Well, if you're talking 1080p, so an 1 HD frame, that's 2 million pixels. And from these 2 million pixels, we have to store at least 3 byte, 4 byte if we use transparency. So we end up with approximately 5.3 megabyte. Now that doesn't sound much, right? I mean, come on, 5 megabyte. That downloads really quickly, even on a German mobile internet connection. But if you look at this one, this was the rage, right? Once upon a time, I was so jealous of all my classmates that had one of those. Oh my god, the Voodoo 2, you just got that one? Yes, for Christmas. Oh my god, I'm gonna murder you and take it. It was the hot shit. It was the thing. It was the best you could get for money. And it has 8 to 12 megabyte memory. Now this is split in 2 things. 4 megabyte to actually draw on a screen, and 4 megabyte to store things that will be drawn on screen. No HD. So time travel just got boring because you can't watch 1080p videos in the past. But still. Then the other thing is, I said the magical letters GPU. What the hell is a GPU? What is it? How is it different from a CPU? Well, if we look at what they do, you see that the CPU generally does pretty much all the computations. It has to deal with all kinds of crap that we as programmers throw at it, right? So we write a really bad program, it has to figure it out. You know, my job is to write it, your job is to execute it, computer. Come on, how hard can it be, right? So it has to do certain things that are pretty tricky, for us humans especially. Multitasking. I can't do that. It's not going to go well when I try that. It also has to figure out how things depend on each other, because we may actually read something from a file, modify it, then do something, compute something on this modified value and write it back to the file. And then another program might read from the same file, gets the modified value, modifies it again, writes back. So it actually has to figure out what are we doing, right? And it has to switch between different programs that have nothing to do with each other. And the problem is that they have to somehow figure this one out. And they went like, you know what? So we want to run as many instructions as possible. And the thing is, normally reading from memory or reading from a disk or even reading from a network is so slow. So we cannot deal with that. We optimize for just running things that we already know we have. And we run these really quickly. But then you have graphics. In graphics, all you do is pretty much just I/O. I have a bunch of ones and zeros and I want to put them on screen. That's input, output. There's nothing happening besides that. Asterisk. There's a bit more involved, but the thing is, you actually don't need the optimizations that the CPU needs. You need other optimizations. And then you think about it like, so for a computer it's fine if it just runs like, I don't know, a million things in 1 second or so, because that's really, really fast. 1 million calculations in 1 second is kind of fine, especially if reading or if writing to the network takes 5 seconds, then this 1 second isn't too bad. But if you try to do 2 million pixels 60 times a second, you have 15, 16-ish milliseconds to run 2 million operations. It's a very, very different scale. We're talking orders of magnitude difference. And that's why there was this thing called a GPU, which is specifically optimized for that. Because they figured out, actually, you know what? A pixel on screen doesn't need to know about the other pixels on screen. I just have a pixel and I put it in. A computer program on the CPU might figure out, oh, this screen shall be green if this other screen is red. But I, as a GPU, don't care. I just get like green, red, green, okay, fine. So I can basically just have a lot of processors that take data, transform it, and output it, because it doesn't depend on other data. And there's no such thing as context switching. It looks at the memory and it puts it onto the screen, full stop. I don't care if the pixel I put on screen is your calculator or Facebook. I don't care. As a GPU, do whatever you feel like. So we have a highly, highly parallel architecture, and we have a unidirectional data flow, because there's the screen. Once the pixel is on the screen, I, as a computer, am done with it. There's no way something comes back. While in a program, I get a return value, and then I have to do something with this return value and all the jazz. So the GPU basically doesn't care. It's highly optimized for these parallel I/O operations and highly parallelized for floating point operations on colors, for instance. Now we could say, that's it, that's all you have to know. But actually, let's go a bit deeper. So GPUs. The GPU runs programs as well. Our CPU runs programs, but our GPU runs a special kind of program. If you wish, it runs functional programs, and lots of them. It runs functions. It gets data from the memory, it does something, some computation, it runs a function with these parameters which come from memory, and the return result straight goes onto the screen. And that's it, end of story. So it's really, really functional. You could basically write it as an arrow function. You have a bunch of inputs, which is the pixels and the colors, and one output, end of story. So someone thought, you know what, we actually kind of can squeeze that into a really, really small kind of circuit and put lots of them together. So they actually built these things called shader units. We're going to see exactly what they do later on. But basically, they are small processing units that run functions really, really fast. And you put thousands of them together. So now instead of just running 1 pixel at 1 clock, you run 1,000 pixels. And for instance, the NVIDIA GeForce GTX 970 has, I think, 1,660 something. So this is really, really nice. And that's where VRAM comes in. Because if your VRAM is a specific part of the memory and not just any memory, you may actually get memory that is specialized for actually writing whatever and then reading really fast. And that's really handy, because this thing needs to sort of read data really, really fast and output data as fast as it read, but not to memory. It outputs it to the screen, which is as fast as electrons go. And you work, also interesting thing, you work with very specific data, right? If we look back at how the memory looked for our screen, it's just a bunch of numbers. They are usually represented at floating point numbers because they are easier to work with in certain circumstances. So we don't care about strings. We don't care. We don't care about addresses that we have to look up in memory. We don't care. We already have something in memory and we read from that, and we don't care about any of that crap. We read a number, we calculate something, we output it to screen. So we can specialize our powers onto floating point and vector math. So also helps to sort of make it more powerful. With that out of the way, let's actually paint some happy little pixels. And that brings us to the warm-up part. So first of all, we need to get pixels to actually shine on screen, right? So basically, we just write some color into the memory. The graphic card picks it up and puts it onto the screen. Done. That's rather easy. But now lines are not as easy. How do you do lines? Well, you sort of have to. The problem with lines is they are not one or zeros, right? They can be any sort of shape and any angle, and if you have done math, you know that there's infinite amount of angles that you can theoretically draw, but we have pixels. So what do we do? Well, what we can do here, so we want to have a line from here to here, and I should have colored that differently. So how do we know how to get from here to here? There's algorithms that basically say like, okay, so I'm really, really far away from this point in this direction, so I go in this direction. Now I'm not as far away in this direction, so I go this direction, and so on and so far, and you end up with a line. Hurrah! This is just one of the many algorithms that exist, but it's the most popular one, and you basically implement that in university, and you go like, whoa, I know computer graphics. And the cool thing is when you do lines, you can actually also do triangles, because triangles are nothing else than 3 lines between 3 points. And that's really cool, because triangles, when you use enough triangles, you can basically have any shape you want, right? If it looks shit, you're not using enough triangles. It's like violence, right? If it doesn't work, use more. Actually, no, please don't. Or Java, right? If Java doesn't work, just use more. Definitely gonna work. Siemens had to recall a train prototype because it was using Java. It's a high-speed train, and if you press a button in the cockpit, it takes 1 second until it actually does the thing. Going 250 kilometers an hour, that is a bad thing. Anyhow, so yeah. We have 3 points. We want to put lines in between them. We know how to do lines. We can do triangles. Hurrah! So now we actually are filthy rich because we can draw everything. However, we are only drawing line skeletons, right? So what if we want to sort of color this one in? Also, there's algorithms. Hurrah! We just pick any point that is in the triangle, and that's rather easy to calculate. And then we check all its neighbors. We go like, okay, so this is already filled in, this is already filled in, this is already filled in. Oh! Fill this one. So this is already filled in, this is already filled in. Oh! And oh! So fill them. And we continue. Hurrah! Now we filled 9 pixels in 6 clocks. That's not really good, is it? And each time we had to check 4 different memory values, and there's better ones like the scanline algorithm that I'm not going to explain, but basically what it does is it looks in between and just fills everything until it hits one of the same colored, and then it goes on and sort of fills in more quickly each step. So now we can fill shapes. Cool. But now it looks crap. So what do? There's a thing called filtering. So in this case, for instance, we have this really, really crappy A, and we turn it into a less crappy but also very blurry one. And we feel much better about this. And if we don't do this, clients complain. And if we do this, clients also complain. So yeah. But you know, people keep saying this is better. So okay, we make it better. But why is it actually better? Well, if we look at it, so here we have the same line as beforehand. This time it's colored in blue. But you can see in the red ones, these are the ones that we touched and actually haven't filled. So we are making errors, we are making mistakes, and we have to sort of fix them again. But we can't just make them black, because if we just also make these blue, it still looks crap. So what do? Well, if you look at it from a different perspective, if you look at it as a signal, as how the human eye perceives the light, one of the problems with these lines, with these really, really blocky and pixely lines, is there's not very much going on in between. So this is 0, this is black, and this is white, but there's not much in between going on. So my eye basically sees like nothing, 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 everything, nothing, nothing, nothing. And that's a problem for our eyes. So what we do is like, we go like, nothing, 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 something, 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 more, 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 now everything. And it's like, okay, that's better. It's still pretty harsh, but it's better. So that's basically what you do. But this obviously takes some calculation time. So now we know how to draw things on the screen and how to make it look nice. Let's see how the browser does it and how we can make this effective. That's it. No, just kidding. So basically, you start with a tree of elements. That's our DOM. Who has never heard of DOM before? You never know. And the browser then goes like, okay, so I have this document object model, and then it parses the style sheets or style instructions that are in there, and basically figures out, okay, so this has a font size of 16 pixels, this is bold, yada yada yada, and it creates a render tree. So basically it goes, okay, so everything here has 16 pixels font size. This one as well, but this one is also bold, so hello and students actually have to be bold, and the div here and the image here also font size 16 pixels, and it should be floating right, so I know how to sort of make it happen and make it look. But there's still just a tree. This is still a data structure. We still have to turn this into pixels. Now this is what happens. So basically the browser goes in, gets the DOM, parses the CSS object model, parses the document object model, creates this render tree, and then it layouts. Layout means it goes, okay, so I have my body here. It has a certain size, which is depending on the window that I'm operating in. I know that I have to make everything here 16 pixels large, and so that means I also have to put this div in here, which has a div in there, which has the text, and this text is 16 pixels large, and plus maybe this div has some padding, so and it calculates, and this is what layout does. And it's really, really expensive actually, because it has to do this for everything that comes below, because if I now insert something on top here, then it has to sort of shift this entire thing down and recalculate everything. Or even worse, if I click on this one and the JavaScript changes the CSS for the body, it also has to go through everything here. It has to start here, make this larger, make this one larger, make this one larger, change this one possibly, and then it's really, really expensive. So you want to avoid layout. But what happens after we have done that? Well, it actually puts it onto the screen, and this is this paint that happened here. And you can see something interesting. So now we have a really, really large window here, but it actually doesn't paint the entire window. It only paints the bits and pieces that have changed. So here might have been a change. Maybe I clicked on something and this text appeared, and then it only repaints the bits and pieces that it actually has to repaint. But how does it know that? Well, first of all, there's paint order. So it goes like, okay, how do I actually paint these things? Well, I start with a background and with a color, because it's kind of the basic thing that I fall back to if the image doesn't load, because at this point I might not know if the background image loads. Then I put the background image on top of it. Then I put the border color around it. Then I put the children in, and then I draw the outline. So that's the order. This is specified. I'm pretty sure some browsers ignore it anyways. But it still does not know how to sort of contain the problem, right? And here is an example if the GIF does what it should be doing, but apparently it's not. Here would have been an example where if I change certain bits and pieces, there's a setting in the developer tools that allow you to see which areas are being repainted. And it goes, you know what? I kind of think from the way that the CSS is laid out that I sort of have to, you know, put this onto a separate layer because this might change. But you know what? This thing here doesn't change, so I just put it onto a different layer. So what happens next time when this thing gets larger, it doesn't have to lay out the entire page. It only relayouts this bit. And that's cool, because then I only have to paint much less pixels, probably like a quarter of the amount of pixels that I had to paint if I would have to paint the entire thing. But how the hell does the browser know when to do this, right? How does it know, and how can I help the browser make these tiles? Because, you know, in the end, you know best what's going to change. How does the browser know that? No, well, there's now a proposal for, actually, it's a standard draft, I think, that's called will change. It's a CSS property that you can set and say like, hey, by the way, this element is going to change. So the browser has even more hints. But one of the easiest thing is to understand that to get a layer, to get a tile, it creates layers, and layers basically mean you have one element or a bunch of elements separated from the rest of the flow. And how do you do that? Well, we're going to see that later, but what does it actually give us? Well, what it gives us is the possibility to sort of make an image out of it, right? So if we look at the example again, this thing here, for instance, if this changes, and it's a bit hard to see on this beamer, but there's tiles. So here's a tile, right? and here is a tile as well that goes out of the screen. If this or this tile and this tile, for instance, so if the list gets longer, this tile and this tile and this tile will change. This tile because it sort of is badly positioned, and then it actually shifts down and only repaints these. This and 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 so on and so far are saved as images. And all it has to do, even if something changes here, like literally here, and this just shifts down, it basically all it does is it shifts the image down, no repaints, no touching pixels, just moving things down in memory, just copy things down, be good, and recreates another new tile here to actually make this change. So what you do is you basically have a bunch of images. And that is cool because you don't have to sort of repaint everything. You basically just have a piece of paper and shift it around and put in a new piece of paper. Getting this new piece of paper is tricky. If you ever, I suck at drawing. I really, really suck at drawing. For me, getting a piece of paper that looks nice with some stuff on it, hard. But the browser can do it. But it takes time as well. But you know, shifting this other piece of paper, that's rather easy. Nice. So you can also sort of reuse them when you scroll. Scroll performance. Who had issues with scroll performance? Hands up. Yeah, it sucks, isn't it? And that happens when your JavaScript mixes around with how the page looks and sort of changes these tiles. Because if your JavaScript does some random shit on the website and actually changes all these tiles because it's like, oh, on scroll we're going to change the background color to a random color every 60 frames. That's a bad idea because the browser then has to repaint the entire thing. And if you scroll, it knows, you know what, it's just scrolling, so he's not actually touching the website content. So I can just use these images that I have and just, you know, move them around the screen much, much faster. Same for maximize, minimize the window. Ah, here's the actual, aha, okay. Now you can see that the green flashing areas are the areas where the browser goes, okay, I have to repaint this. And this is reasonably good. So for instance, it doesn't really touch most of the tiles. It actually is clever. Chrome is clever enough, and Firefox and Internet Explorer, they're all clever enough to figure out when not to paint the entire tile. They have to rechange the bitmap in the background, but actually they only repaint the areas where I actually change bits and pieces. So use this feature to figure out where you screw up. Because if the entire page starts flashing, then you have a problem. And here is how you contain changes in layers. So here I use, for instance, this is this is relative position. This is absolutely position. And you can see this one has a trace of green happening around it when it jumps. This one doesn't. You know why? Because this one doesn't get painted. There's no painting happening. It's just moving things around, literally. No painting, no nothing, really fast. Now, both of them look kind of okay, but try to do that with more complex examples and it's not going to look good. So there's that. Yeah, so how do you actually make layers? This slide is one of my most feared slides because browsers change their behavior all the time. There's certain things that kind of stay the same. For instance, video, canvas, or flash will always be, or Silverlight, or whatever else you think it's a good idea to embed into the web. It's not. Gets on its own layer. Why that? Well, if you think about it, a video is very, very likely to change very, very often. So it's a good idea to sort of put that onto a separate layer and not change the page under it or around it. So you want to contain the change that happens there. For objects, obviously more or less the same reasoning. Canvas, more or less the same reason, because on canvas you can draw stuff, so you're going to change pixels. So to contain this amount of change that the browser has to do, it uses a layer for them. Then there's other things that are kind of known for many people know this one. You can hack it by saying like, yo, you know what, I'm going to do transformations. I'm going to change this element. I'm going to, I don't know, rotate it, or I'm going to scale it up or scale it down or skew it or do some really crazy stuff with it. In this case, we do crazy stuff in doing nothing. But the good thing is it still creates a new layer. So unless you don't know what else to do, you can do that, right now at least. For instance, if you know, okay, I have this list, and I have hover effects in this list. So for whatever reason, when you hover over a list item, it does something. It scales up, or if it changes color or something. And you have a really long list, and people do that all the time. And yes, people do this. For whatever reason, they should actually get a hobby or go outside and play with their kids. I don't know. But hey, people do that. People are people. I'm not going to tell you what to do or not to do in the browser. But yeah, they do this, and then it has to change a lot. And actually, it re-renders the entire freaking page all the time. It's going to get really, really slow and really, really nasty. And then they go like, look, I do this, and then after 5 minutes, I had a bug report like that once upon a time in a different company. I was like, when I do this, it starts going slow after 5 minutes. I'm like, okay, but why? Like, how is that a problem? Okay, fine. Enough ranting. Not really. There's gonna be more ranting. No worries. There's never gonna be no ranting. I can rant around the visa process all day if you wish. And anyway, so yeah, so you can then use this to sort of put it onto its own layer, and then if each of these items, for instance, is on its own layer, it's just gonna repaint the small layer, and it's gonna be nice and fast. And even after 50 hours, this person that has nothing else to do than report bugs like that will still keep doing this. Like, I bet after 72 hours it's gonna fail. Anyway, and he will be wrong. So, CSS animations for some properties, not for all of them. So if you hear someone say like, oh yeah, CSS properties solve all your problems, be really, really careful, because it's not quite true. So for instance, animated transforms, transforms 3D, so if you animate something by, like, I don't know, flipping it or something in a CSS animation, that is fine. If you change its width, for instance, not so fine. Because that's not going to create a new layer. That's still just going to push things around, because it's still in the same sort of layer, it's still in the same flow. Unless you make it like position absolute, then it's not in the layout flow. Then the browser doesn't have to shift things around. But if it has to shift things around, tricky one. So no layers there, but layers for certain properties. Also, if children are on a separate layer. So for instance, if I have a div around a canvas, it's very likely that this div also gets its own layer. I have not found any explanation for this, but okay, you know, there will be a reason. I actually bothered a bunch of people, and they're like, it says so in the spec, I think. I'm like, okay, valid reason, I guess. I mean, after all, you know what? I only got my visa last night, basically, because I had an insurance letter that says global coverage unlimited, like unlimited amount of damages will be covered worldwide from my health insurance. And the embassy wrote me back like, yeah, but it doesn't say at least 10,000 in Belarus. What? But valid reason, can't fly in. Another reason when the browser, or another moment when the browser creates a layer, is when you fiddle with Z indexes. Z indexes are freaking complicated, even though they don't look like that. Be really careful to understand the spec, because I don't, and I always get hurt by it. So, tricky one. But they create new, because the stacking context changes, so it has to sort of figure this one out, and then a complicated reason. So why are we not just making everything a layer? Unless you have unlimited memory, you shouldn't. Because, you know, running out of video memory is really expensive, because you know what's going to happen? When you run out of video memory, it's going to swap into something else. And most likely, it's going to swap into some random pieces in RAM. And then it has this problem of, so basically what the operating system tries to do is it tries to get one big block of memory for your graphics card. Or your graphics card has actual memory. But if that fails, it has to talk to your motherboard first. Like, oh shit, it's not in my memory. Hey, over there, can you give me that value that I need to get this pixel on? A long time nothing happens, like with my health insurance when I try to get a new letter. And then at some point they come back, and this is bound to be really, really slow, and it's really, really hard to detect. You have no way of detecting that, and you have no way of sort of preventing it. So better lean on the conservative side and not make too many layers. Also, upload to VRAM actually takes some time, because this is the moment when it has been painted, but now you have to transfer this entire blob back into the VRAM. And this is actually happening in your main thread. And actually, no, it's not happening in the main thread. It's happening in the render process. But still, it's pretty expensive. And it's not too expensive because you usually only do it once, and then you're done for quite some time. But if you have a lot of layers, it's very likely that they're going to change all the time, and then actually it's going to repaint and upload and repaint and upload, and then it's going to be slow again. Okay? So be conservative. Do things where it makes sense, where it's really necessary, where it's essential to change bits and pieces. Also, as I said, you never know how much VRAM there is. Fun fact, on old OS X versions, on certain, not on all, but on certain iMacs, because you don't know how much video RAM you have, especially when you use WebGL, you can just write things into video RAM and crash the entire computer. It's hilarious. It's a wonderful conversation to have with your client. Your website just crashed my computer. I admire your problem. I don't have a solution. Bye. Okay, enough CSS. Now to the more visual bits again. Canvas. Canvas is cool. You know why? Because we get a layer for free. Haha. Well, it's not for free, but hey, we get a layer without doing magical things. Also, we get direct pixel access. So try to render a graphic with CSS. That's possible. I've seen people do that. There's people like Gregor Adams that really push the envelope there. But usually you just want an API that says like I can paint this pixel, that pixel, maybe make a line, maybe make a circle, maybe paint some text, whatever, and not sort of deal with a bazillion of diffs. Because all that CSS really can deal with is sort of like, yeah, rectangles, right? So it's not so nice. But yet, it's not the most powerful thing that there is, because it has limitations, as everything has limitations. So here we see a chart from, I absolutely have no idea how to pronounce that. It's an operating system for mobile system, devices called Tizen, whatever. Tizen? Tizen. I have no idea how to pronounce it properly. And they actually checked out, so what happens when I have a lot of objects. So here we have 10 objects, 30 objects, 100 objects, 250 objects. And I use Canvas 2D, which is that? Because WebGL also uses a canvas, but uses a different sort of driver behind it. So the 2D canvas, which is the wonderful blue bars, versus the WebGL canvas. And you see 60 frames. We start at 60 frames. Nice. 10 objects, no difference. 30 objects, that's not much. Like 30, I don't know, lines, 30 rectangles, 30 images that you want to draw. You start seeing drops in frames. We're still below, still above 30 frames, which is the magical threshold where it starts getting dangerous. But WebGL goes, whatevs. 100 objects. Ooh. 12 frames, that's visibly Yankee. That's not going to be a fluent motion, that's going to be slideshow style. While WebGL still has a burger. 250 objects, let's not talk about it. So, why is that? Well, for the canvas there's a few things that some people don't know. One is text rendering is horrible. Because text rendering is not so easy to compute actually. It has to load a font and it has to make sure that it traces it out and it has to fill it correctly, and then you have font styles like italics or bold, and it makes it really, really complicated. Drawing rectangles on the other side, that's really easy because I just have a rectangular blob of memory and just done, right? So text rendering on canvas is possible. It's not in itself a problem, but if you basically, I once got the question, once upon a time on a conference that shall go unnamed, which is RSCONF last year, someone asked, oopsies, someone asked if they could sort of build the entire DOM in a canvas. You can. Flipboard does. It's just a horrible idea. First of all, it's not going to be really fast because text rendering is not really good. Like, unless you do pre-rendering and then basically just serve it as a one blob, then it's kind of fine, but the other thing is that you lose all accessibility because the screen reader doesn't see anything. I mean, this is really bad, so don't do that. You can, but you shouldn't. Just like, I don't know, try to get into Minsk without a visa. I still took 20 minutes for the passport control lady to sort of let me through. It was fun to watch. I think she didn't like the sort of going through pages and going, yes. I think that didn't come off well. Anyway, so another thing that you can do is you can draw images onto a canvas. You can even do video, because video theoretically is just a lot of images really quickly in succession. But in fact, if you do something to these images, if you transform them, or if you rotate them, or if you scale them, this starts to happen on the render thread, which runs on the CPU. You're not getting the GPU here. The GPU is really good at that stuff. The CPU not so much, because it does one thing at a time, just very quickly, but it does one thing at a time. So don't do things like really heavy transforms. Do not try to basically repaint the entire thing all the time, because that's going to be slow, and we're going to see that in a second, how that looks. So try to only redraw the bits and pieces that you actually have to redraw, and leave the rest alone. Also, there's functions that actually allow you to sort of save how the canvas looks and then get it back. Also really slow, because this is actually using regular memory and not VRAM and not this, not the GPU. So the CPU then has to sort of put stuff into memory and then wait for you to call you again, and then it actually puts it back. And that's pretty expensive. It works, but if you do it each frame like 10 times, that's bad. Also, there's a thing called draw calls. So every function that you call basically does one thing normally, like putting one, I don't know, circle on the screen, putting one rectangle on the screen, putting one pixel on the screen is one draw call. That means the browser prepares the data, like these pixels have to change, and then throws them over to the GPU to actually do the thing. And this throw over to the GPU is actually also expensive, because it has to exchange from the CPU, so the CPU is involved. And you know JavaScript is single frame threaded, right? So you only do this one thing at a time. It has to throw this over to the GPU, where it then can be parallelly executing all the one things that you gave him. That's a bad idea. Especially when you do things like I draw lines, that's usually paths. So for instance, if you try to draw, I don't know, a triangle, instead of basically trying to pixel them, draw lines. And just don't line, draw call, line, draw call, line, draw call. Do begin path means here starts the data, line, 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 end path. It's one draw call. You save draw calls a lot if you have a lot of triangles, especially. Makes sense. That's the combine paths part. And again, do not repaint the entire thing. Especially if it's large, it has to repaint a lot, because it can't do magical things for you anymore, right? You're on one layer. The browser is out of the game. It's now your responsibility to make sure to minimize the amount of data that has to be redrawn. All right. And here's an example. Here we see the the green rectangle is the entire thing. Because all I do is I start with a position, and I add one to the position, and I make sure that it wraps once it reaches the end. I fill with black. I fill the entire canvas black. Then I put in that the next one should be red. And then I put my little rect in here, and then I do this again. So on every single time, this paints the entire canvas black, and then the rectangle in red on top of it. Now this doesn't look too bad, but actually especially on older phones, this is pretty bad when the canvas is really large and this is not the only object that's moving. So how can we make this better? Now look at that. The paint rectangle is much slower, and it's actually, the fun thing is the GIF exporter is really shit, so actually it looks as crap as before. But trust me, it's nicer, especially on older devices with more things to draw. And the only difference here is, well, I had to trick a bit, because ignore that implementation detail. And I only repaint the previous position of the rectangle, and then repaint the rectangle in the new position. Done. As long as you can do things like this to avoid repainting the entire screen. I know it's hard sometimes, but trust me, it's worth the effort. Reduce the paint area. And you know why? Because this entire thing here, all of this goes into bitmaps and it's not going to be touched. This stays in memory the same. It's not going to be changing, so it's not going to be re-uploaded to the GPU. This bit is, and that's kinda okay. It's not a layer, by the way. This is just a paint rectangle on this layer. it's only changing the small piece of memory. Who here has heard of CSS Blend Modes? A few. Who has used them? Alright, cool. So this is another cool thing to avoid you having to use the canvas all the time. If you want to have certain effects that you can do with things like Photoshop, you don't have to fall back to a canvas. You can do that with CSS, which is quite convenient. So here we have the background image, which is some confusingly called face JPEG. It's not a face, but okay, fine. And a background color red. Now we know from the render order, the background color is rendered first, and then the background image is rendered on top of it. But right now what would happen is that the image would overlay, like it would not show red and then the image. No, it would just be the image, and there would have been red below it. But right? But how can I sort of do something about that and sort of mix the two? Or even better, if I have multiple background images. How can I mix them? And here we have this background blend mode for background, for instance. And we say multiply. That's kind of obvious. You take this, multiply it by this, and you get this. How does that actually work? Well, for each pixel, it goes, okay, so this is the red times the red in here. So this one, for instance, is pretty much black. So the red channel being 1, which means 100% red, times 0 equals 0. Rather easy. And then you get these effects. And this is not the only effect that you can get. You can actually get a bunch of effects, because it's generalized as I take a bunch of colors, and really what happens is obviously for each color it goes red versus red, like red 1, red 2, red, blue 1, blue 2, and so on and so far. And then you get a new color. And colors usually look like this: red, green, blue. 0, 0, 0, black. 1, 1, 1, white. Very simple. And there's a bunch of, whoa, why is that shifted? Alright, anyway. There's a bunch of different functions. We had the easiest one, which is just you multiply pixels by pixels. This is a crazy one. It looks really complicated, but all it does is actually, if areas are really, if areas in one of the pictures are really dark, it gets darker. If they are lighter, it gets lighter. That's all it does. Because you invert the colors, and then you invert them again, and then you multiply them with inverses, and but it actually looks nice often. Overlay does a similar thing. Oh no, sorry, wrong. This does it darken? I forgot what this does, but it's actually quite cool. This here, on the other hand, checks if the color value is brighter than sort of middle red or green or something, and it actually makes sure that then it sort of makes it brighter. If it's not if it's not bright enough, it darkens it. Oh yeah, so in this case, this kind of darkens it, but I'm not sure why I'm confused now. Anyways, so Wikipedia has more. But also I can obviously only darken, so I only take the darker color value of the two, or I only take the lighter one. And I can also sort of subtract them, so if I have, I don't know, white minus green, then I get yellow. So you can do these things. There's much more, and there's much nicer ones like soft lighting, hard lighting, color dodging, all that stuff. Used it once upon a time, got a t-shirt, done. Quite nice. And now to the interesting bit. 3D graphics. 3D graphics is a bit tricky because who here has used WebGL before? Again, have a coffee. So let's start with some words, because we like to invent new words, because it would be easy for people to come in and just use words they already know. First of all, we have this screen here, and we have space in front and behind it, right? So we have 3-dimensional space. This is 2 dimensions, and then I have a 3rd dimension here. I could probably, right? And that's as much sport as I get this month. Anyhow, so you could say it's a point in space, but you know that would be like cheating. So we get a new word. It's called a vertex. A single point in space, this where my fingertip is a vertex. This point in space is a vertex. Just to piss off everyone who's not a native English speaker, vertices is the plural. So one vertex, multiple vertices. cool, now we have points in space, but how sort of make them, how can we make them shapes, right? How can we sort of figure out, I have 10 points, what is this? A bunch of triangles? A really weird, crappy circle? We don't know. So we have a list of points, or basically we have a list of which points in this list of many, many points that we have, in this 10 points, make shapes. For instance, if I see one face is point 1, point 2, point 3, then I know, aha, it's a triangle because it has 3 points. See, vertices. See, I fall for it all the time. And now, that is nice, but if we want to do things like figure out how lighting works, for instance, just imagine this. If I take my jumper like that, the light of the beamer has full effect. It gets brighter because the light shines onto my jumper. But if I turn it like that, it doesn't get any brighter because the light doesn't affect it. So how can I express this in computer world? You do that by using a vector, which is basically just a bunch of values that actually tell you in which direction something points. And this is called the normal vector. The normal vector basically just says which way a face, well, faces. So this is the normal vector for this one, for the upper side of the block. This is another vector, normal vector. And here you see a lot of normal vectors. And you see that they can be used to actually figure out how light works. So you see, this is really dark because the normal vector points away from it. This is pretty bright because it points towards the light, and so on and so far. And then there's a term specific to WebGL, which is called a fragment. If we do anti-aliasing or other filtering techniques, we may actually pretend we have more pixels than we actually have. You remember the graph, right? When I did this and made it bright, pretty wide as well. That was when I sort of pretended I have more pixels than I actually have. And the fragment basically says this is all the pixels that we have to color in, really. Like ignoring the fact that there's effectively like only a fourth of the pixels or something like that. So you get a fragment like this, which tells you which pixels you have to color in. So this is a line, which is tricky, and then we make the ugly blocky fragment from it. Now you may have heard the term shader. Who here has never heard about shader? Okay. Who here knows what a shader is? Again, you know, coffee and stuff, you know the drill. So shaders, if you remember that I said on the GPU, basically what we do is we run a function that takes data in, does something, and gives data out. A shader does something. It's the function. So it's a program that we can write, that you can write, and you can use to actually get data in, transform it, and output it. And there's basically, they're just programs. They're written in a programming language called GL-Slang, graphics library, shader language. And they read data, transform it, write it, and the data is either a vertex, which means a point in my universe of points that I want to draw, or actually an entire fragment that I have to pixel in. And then I get each fragment pixel individually, which is convenient. It has no dependencies, as I said. We have a point, and we sort of move this point around. There's not be any sort of like dependencies or something like that. We can ignore that. It runs in parallel. It runs really fast. Shader units execute them, as I said, 1,664 shader units. Approximately 1,664 shaders run in parallel. So a lot of functions are being run in parallel, which is nice. And there's two general kinds of shaders. One is the vertex shader. Duh, right? It's taking a vertex and does something with it. And usually what it does is it does things like projection. So I don't want to figure out, like, I just want my world to be somewhere. Like, I want this point to be here. But it depends on where on the screen it is. It depends on the camera. If you think about it, if this is my camera, this point is off screen. But if I shift my camera like that, it's straight in the middle of the screen. And you know what? You don't want to change this all the time in memory. You want this to happen right before it actually gets rendered. So you make the sort of the graphics card, the shader unit, do the work for you. So the shader unit takes this vertex, which is always over there, and takes some other things like where the fuck the camera is, and then figures out like, okay, so I actually have to, so the camera faces this way, but the point is over there, so I have to change it, like I have to rotate it like that, and I shift it like there, and ta-da, it's in my camera, where it should be. So that's perspective projection. You can also do things like make things wobble or make things distorted and all kinds of weird things. Then there's fragment shaders. They take a bunch of pixels. They are run for every single pixel that will be sort of turned into a color on screen. So they take these fragment positions and a bunch of other things and draw something on screen. In the simplest case, it just takes the position and outputs the same color for every one of them. It's an easy shader. Also, fragment shaders are used to figure out how far away something is on the screen, right? So it can actually calculate that for you too. You do interesting things like the lighting, for instance, that I said is one shader that is a fragment shader, is how does the light reflect or actually shine onto a thing. This is where it happens. Another thing is if you want to do stuff like complicated reflections, lens flares, high dynamic range, because you can manipulate the colors, right? So you can run pretty much the blend functions, if you wish, on colors and get the right colors onto screen. Nice. And this is how it looks. So the blue boxes are JavaScript, and they're kind of easy territory. I start with my vertices with all my points as an array, and I start with another array that tells me how these vertices belong together. And that's all I do. And then I do magic with WebGL. I basically say like, hey WebGL, take these arrays. And everything in green happens on the GPU. So we get the full pipeline. The buffers are basically just these arrays put into memory on the graphics card. So this is where it actually uploads it to the GPU. And then the Vertex Shader runs, which is the program that shifts the points around. The rasterizer is a thing that is on the graphics card and figures out how to sort of make pixels from that and make the fragments from it. The fragments go into the Vertex Shader, and the Vertex Shader actually produces a bunch of colors that get drawn onto screen. Nice. And this red box here is the shader code. That's the programs that you can write to make this happen. You can't mine bitcoins in WebGL, but hey, at least you can execute some code on the GPU, which is pretty cool for a browser, really. And for instance, Canvas does not give you this. Canvas does not allow you to touch this or this or this. All you get is basically a buffer and a predefined set of these, and you get pixels onto screen. So this entire power here with the shaders is only available to you if you run WebGL. That's the biggest difference. This is truly GPU accelerated. The other one is also accelerated because it uses the GPU to give you access to the pixels, but it doesn't give you access to the entire pipeline. By the way, what does it actually buy you? Well, it buys you things like if I want to rotate or if I want to do blending, like color blending, I can do that entirely on the CPU because I do it at GPU. I do it here or here. And I have nothing to do with what the browser does or what the CPU does because it's not in the same environment. This is really, really nice. So if I want to scale a thing, that goes into the Vertex Shader and I'm done with it. If I want to sort of invert colors, that goes into the fragment shaders and I'm done with it. And these do the work really, really quick because they do it in parallel. Versus what I have to do myself if I go through the canvas, because I don't have these powerful things here. Not entirely. You have some access to it, because obviously the scaling functions do it, but in a limited way. So for those of you who have worked with WebGL, some performance tips and tricks that I learned while working with WebGL, because at Archeologic our product is entirely WebGL pretty much. And we learned how things work and how things don't work really quickly and really painfully. One such thing is if you deal with reading data from network, for instance, or reading data from wherever, really, you'll want to avoid having to convert them between whatever JavaScript thinks it is and what it actually is. So you want to use typed arrays, float 32 arrays, in fact, to make sure that there's no conversions going on anymore. You also want to make sure that it's in the right format. So you want to make sure that basically you get the data and straight away upload it to the GPU, because if you have to convert anything before that, that's going to happen in the CPU. That's going to block your main thread. That's going to make everything horribly slow. So this is one way of actually ditching that problem. There's techniques such as level of detail, because obviously, just imagine you have a really, really cool spaceship with really, really nice textures. They look great, but they're 1024 by 1024 pixels large. That's a lot of data. And it looks really cool, but the spaceship is like a light year ahead of you. So it's 5 pixels. Do you really want to load the entire huge image to display 5 blue pixels? That's a bad idea. So level of detail allows you to figure out how far away is this thing, and then uses a technique called MIP mapping to actually load the smaller one. You load a small image and display that, and a small image means not so much data. So you only upload, instead of uploading 500 megabytes at some point, you might upload like 1. And that's a big difference, and it makes a big difference on network as well. Especially when you're on mobile and on a data network, you can feel how the money is not flying away of your pocket, which is cool. Also, lighting is really, really hard. So for making lighting, I have to figure out how reflective is this? What color does it have? And then where's the light? Where's this thing? So unless the light is moving all the time, obviously I have to sort of figure out this ray goes like this ray goes like that, and I have to recalculate this, and it's really expensive. But here, for instance, light is fixed, surface is fixed. Why do I bother? Why do I recalculate the light all the time? There's a thing called light map. So I know the light is there, I know the surface is there. I can have a server-side process render it once into an image. And then I load an image, and this image is grayscale. And where the image is white, I make this brighter. Where the image is black, I make this darker. Done. No further magic has to happen, no further ray casting, no further very complicated math. You basically just do blending again. Light maps, really useful. Also, if you have something that has structure and is really, really detailed, do not bother to actually 3D model it, because you're going to have to put a lot of vertices in. And a lot of vertices means you need a lot of shaders to actually process them. So just use as few vertices as you can and make textures that make it look like it's sort of like indented or outdented, like crumpled paper. You can sort of fake how it looks with using textures again, using images. Use images as long as you can, and only do calculations when you really, really have to. Also, normals, we know we have to figure out where a thing is facing. You can pre-calculate that and store it as color. It looks fun, and actually it works really well because you don't have to calculate them all the time. You have them encoded in an image. Really cool, especially for larger models and lots of larger models. And again, still minimize the draw calls. So if you have an office with 500 chairs, as long as these chairs are not going to move, make them one large blob, basically. Make them one large thing and start like, this triangle, this triangle, this triangle, this triangle, this triangle, first chair done, this triangle, this triangle, this triangle, this triangle, second chair done, and so on and so forth, and then draw them all in one go. It makes sense. It helps a lot. There's things that help you with that. So for instance, here you see a large amount of monkeys, or monkey heads, and what they do is they use an extension called angle instance arrays, which may not be enabled on all devices, but if it's enabled, what you do is you say, I have this monkey, upload that once, and then you say, and by the way, this monkey that you just saw, also draw it in these 500 other positions. No uploads happen, the draw calls get minimized. Amazing performance win with not that much work. So if you don't know what to do over the last couple of days, weeks, months, years, the problem as I formulated is I have 50 minutes and not 6 months. So I had to gloss over a lot of details. Sorry for that. Find me if you want to talk about any of the details. I hope I can remember them because I had not that much sleep. These links help you a lot. The slides will be online, are actually online right now. Thank you very much. I have no idea how I did on time.